Fine. So let me go back here to my presentation. So last time I talked about the 4-bit carry look ahead adder. By the way, the adder is not included in this first midterm in the midterm exam. Okay, it will probably be included in the final exam. So we have seen the carry look ahead adder last time. So the reason why we have the carry look ahead adder is that I really would like to make the adder to I would like to speed up. I would like to have a fast adder. So the problem with the ripple carry adder, as we have seen last time, is that it takes time to propagate the carry from one full adder to the next. So if I would like to go back, okay, just to recap what I talked about last time. So the problem with the ripple carry adder is that you have to propagate the carry from one full adder to the next full adder. And this propagation delay is going to increase, okay, according to the size of this adder. So if you are adding n bits, so if A consists of n bits and B consists of n bits, you can see that n is part of the delay. Is going to increase linearly with n. So in order to reduce the delay, if you would like to design a high-speed adder, an adder that actually can do the addition faster than the ripple carry adder, you can design it, okay, like a carry look ahead adder. And I talked about this last time, so I'm not going to spend time today on it. Alas, I'm going to skip these slides. Okay, so we use something which is called carry generate, and we have propagate. The carry generate and the carry propagate can be based on the inputs only, and they do not depend on the input carry. So they depend on AI and BI. These are the bits in my inputs, okay? And it does not depend on the CI, which is the propagated carry. So we don't really want to propagate the carry. So we would like to generate a carry if AI and BI are both equal to 1 and 1. This is my generate signal. And I also have a propagate signal. I would like to propagate if one of them is a 1, the other one is a 0. So we use the XOR. And then we can have the equations, okay, for C1, C2, C3, C4. I talked about this last time. Go back to my last lecture. And then we can design a 4-bit carry look ahead adder as shown here. So all the generate and propagate signals are produced at the same time in parallel. That's the beauty about the carry look ahead adder, is that you can produce, okay, all the generate and all the propagate. So G0, P0, G1, P1, G2, P2, and generate 3, propagate 3. So all of these are produced at the same time. And because they are produced at the same time, okay, so they have exactly the same delay. So it does not depend on how many bits you are adding. You can produce them in parallel at the same time. And then we use the input carry C0 to generate C1, C2, C3, and C4. Okay, so we generate all of these carries using this look ahead carry unit. Okay, so go back to my previous lecture to understand what I talked about last time. And there is also a group generate, and there is also a group propagate. So there is an equation for the group generate and the group propagate that does not depend on C0, that depends only on the input bits. So if these bits are going to generate, okay, a carry, so we call it group generate. So we'll have C4 is equal to 1 regardless of my input C0. Whereas a group propagate, it means that, okay, so these bits are going to propagate C0 from the input to C4. So we propagate C0 all the way to C4. That's called a group propagate. And there is an equation for a group propagate. Now, this is only for 4 bits, just adding 4 bits plus 4 bits. So it's a 4-bit carry look ahead adder. If I would like to design a larger adder, like these are the details of the look ahead carry unit. And here I went into the details of the longest delay. Like, if I would like to build a larger adder, a 16-bit carry look ahead adder, I can go to 2 levels, okay, of look ahead carry units. So I can have level 1, which is inside the 4-bit carry ahead adder. And I can have a level 2 here, which is used across all of these. Notice that how I'm breaking down the inputs. So I have here A3 down to 0. I have here A7 down to 4. So these are called here bit vectors. So they are called bit vectors. They exist in Verilog. I don't know if you have seen them in the lab. So these are bit vectors. So I'm going to divide my input A into bit vectors. Okay, so we have here, okay, into 4 bits. So I have 16 bits here for A, but I divided them into 4 groups, if you would like. Okay, so I have 4 ranges, from 3 down to 0, from 7 down to 4, from 11 down to 8, and 15 down to 12. The same thing is done for B. So I'm using here 4, okay, 4-bit carry look ahead adder to add all of these bits and to generate the group generate and the group propagate. So I use group generate and the group propagate for a second level, level 2 look ahead carry unit, to generate C4, C8, and C12, okay, and C16 as well in parallel. Okay, it will also have a group generate and the group propagate for the 16-bit, okay, carry look ahead adder. So this way I can build a fast, okay, 16-bit carry look ahead adder, okay, hierarchically, okay, using 2 levels. And if you would like to make it larger, we can even go to a 64-bit carry look ahead adder, as shown in this slide. So we have here 4 16-bit carry look ahead adders, as we have seen in the previous slide. So we replicate this 4 times, and we use a level 3 look ahead carry unit, exactly the same look ahead carry unit that we have seen in the previous slide. So we use a level 3 to generate C16, C32, C48, and C64. Anyways, this is not described in your textbook. I just thought about talking about this. This is like an advanced adder, a very fast type of an adder. Okay, so I thought about talking about it. Okay, just to mention it briefly. Okay, but you have all the details in these lecture slides. Okay, so it's like a 3-level, okay, of a carry look ahead adder to implement a large 64-bit carry look ahead adder. So this is what exists really in computer systems today. You have really a very fast adder that can do the action very quickly. Okay, but rather than propagating the carry from one full adder to the next, this will take a long time, okay, to produce the final sum bit and the last output carry. You can do it this way much faster using a look ahead carry unit, and you can actually have it hierarchical at different levels. Okay. Fine. So that's it about the carry look ahead adder. Do you have any question about this topic? So as I said, I went slightly more than what exists in the textbook. In the textbook, they only mention, okay, the 4-bit carry look ahead adder. It is just the first level here of the look ahead carry unit, and that's it. And these are just 1-bit adders. You need actually 4 of these to produce 4 sum bits from S0 to S3. And the carries are generated in parallel so that we have a fast way to generate these carries without the need to propagate them, okay, from one full adder to the next full adder. Okay, so it's slightly more complex type of an adder, but it's faster than the ripple carry adder. Right. So my next topic will be about signed integers and the addition and subtraction of signed 2's complement numbers. Already I talked about signed integers at the beginning of the semester. Okay. So we have seen that we have several ways to represent a signed integer, like signed magnitude, the 1's complement and 2's complement. So this is a quick revision of what we have seen at the beginning of the semester. And today we use the 2's complement representation. So the 2's complement representation is widely used to represent integers. So computer systems use the 2's complement representation because it has many advantages over the signed magnitude and the 1's complement. So I talked about this at the beginning of the semester. This is just a review. I talked about the 2's complement representation. So go back to my previous lecture, okay, in which I talked talked about the 2's complement representation. It's the standard way to represent signed integers inside a computer system. So today, computer systems, they use the 2's complement to represent signed integers, positive as well as negative. So the way that you calculate the 2's complement of any number A, you look at the 1's complement. The meaning of the 1's complement is that you invert all the bits. The 0 becomes a 1 and the 1 becomes a 0. That's the 1's complement. But then you add to it plus 1 to make it the 2's complement. So you take the 1's complement and then plus 1. So this is the 2's complement. And we have seen many examples. So if you would like to take the 2's complement of this number here, what you have to do is that you have to invert the zeros and the ones. So this 0 becomes a 1, the 1 becomes a 0. So this is the 1's complement. And then you add plus 1. So this is the 2's complement. Okay? Any questions about this? This is the 2's complement representation. Now, mathematically, you can show that if you have n bits, yani if the number A consists of n bits in binary, okay, if you are using n bits to represent the number A, so when you take A plus the 2's complement of A, if you add A plus the 2's complement of A, you get 2 to the power n. This 2 to the power n is the final output carry. And if you take any number in binary and you add to it its 2's complement, you get zeros plus a carry. So this carry is 2 to the power n. So you can think about the 2's complement of A as the negative of A. Okay? So if A is positive, the 2's complement will give you the negative value. If A is negative, the 2's complement will give you the positive value. So remember that the 2's complement is like negation. So the 2's complement of A is minus A. And when you add them in binary, you get zeros, you get n bits, which are zeros, plus you get a final output carry. This final output carry is 2 to the power n. So this carry bit is not really part of the sum, it's discarded. Okay, that's the final output carry. I have examples here about how you can compute the 2's complement. So as I said, step number 1 is to take the 1's complement, invert every bit. Number 2 is just adding is plus 36. You take the 1's complement plus 1, you get this number. This number must be negative 36. Okay, that's how you compute the 2's complement of a number. Now, if you add the 1's complement plus the plus, so if you add a number plus its 2's complement, you should really get 0 and the carry. There is another way to calculate the 2's complement of a number, is that you start at the least significant one. Yani this is actually bit here is the least significant one. You skip the zeros. So again, this is plus 36. Skip the zeros that appear. Okay, these are the least significant zeros. Skip them until you reach the least significant one. Keep the 1 and the zeros and complement all the bits that appear to its left. So this is the least significant one. We only complement these bits that appear to the left of the least significant one. If you complement them, you get negative 36. So this is another way. If you are doing it by paper and pencil, this is a quick way to obtain the 2's complement of a number. Do you have any question about this? Okay, we still actually, it's not really time yet. So that's how we compute the 2's complement of a number. We have seen the properties of the 2's complement. Okay, for example, you have the range. You can go from negative 2 to the power n minus 1 to positive 2 to the power n minus 1. Okay, so for example, if n is equal to 8 bits, the range will be from negative 128 to positive 127. Okay, the nice thing about the 2's complement, there is only one zero. We don't really have plus 0 and negative 0, like in the case of the sign magnitude or the 1's complement. We have two zeros, plus 0 and minus 0. So here we only have 1 0, and it is represented as all zeros in binary. And the meaning of the 2's complement is just the negative of A. So if you take A and you add to it the 2's complement of A, you get 0. Because n, which is the final carry. And I have an example here. For example, this is plus 44, represented in 8 bits. This will be minus 44. This is the 2's complement, which is negative 44. If you add plus 44 plus negative 44, you get 0. But there is a final carry. So you get actually 8 zeros in binary. So that's my sum in 8 bits. Plus you get a carry. But this carry is 2 to the power 8 because we're using 8 bits. So this is my 2 to the power n. But this final carry is ignored. Okay. So these are the properties of the 2's complement. Now, I only have a few slides left, but I'm running out of time. So let me pause here. I will continue this, inshallah, on Sunday. I thought I can finish this topic, but we took a lot of time at the beginning. Anyways, no problem. Okay, so this was a good lecture. Let me stop recording.